Alright, today we're going to learn how to do the orbital diagrams. We're going to use this particular diagram. You'll remember that they go from lowest energy to highest energy. And we're going to use the three rules that we talked about. We're going to fill lowest energy before the higher energy. So we're going to fill from the bottom up. The second rule is that they have to have opposite spins. So remember, each of these little lines represents an orbital. And one of the electrons has to be spinning up, one has to be down, opposite spins. Okay, we're going to depict that by having arrows showing the different spins. And then the third rule was that each orbital of the same energy level has to be filled before going back and pairing. So let's look at the P's here for an example. P's have 3 orbitals at the same level of energy. So when we're filling those, the px has to have 1, the py gets 1, and the pz will get 1 before you can go back and pair. After they're all filled, if you need to fill in more electrons, then you'll go back and fill in the second one for the px, the second one for the py, and the second one for the pz. And hopefully you'll see that as we move through and do some examples. So let's go ahead and do some examples. First of all, we're going to do one with 4 electrons. And you might think, well, what atom are we actually doing if we're doing 4 electrons? Well, remember, in a neutral atom, the number of protons equals the number of electrons. So in a neutral atom, if there are 4 electrons, there are also 4 protons. We can use our periodic table and see which element has 4 as its atomic number, which tells us the number of protons. And we find out that that's beryllium. So by doing an electron configuration for an element that has 4 electrons, we are doing the electron configuration of beryllium. So let's go ahead and do that. We're going to start at the bottom, and I'm going to count as we add them in. 1, 2, 3, 4. Hey, we're done. So yes, all these other orbitals are present, but they don't house any electrons. Okay? The only ones that we're really interested in are the ones that have electrons in them. So writing this all out as a figure takes up a lot of time and a lot of space. So you can imagine we want a shorter way of doing this. So one way of doing it is to just write out the orbitals that are occupied. So we're going to write 1s, that tells us which orbital we're talking about here. And it has 2 electrons in this orbital. So we're going to write a superscript of a 2 in there. Then we look at the 2s, and it also has 2 electrons in there. So we're going to put a 2 up there. This is the electron configuration of beryllium. Okay. Now let's go ahead and do one with a little bit more meat to it. We'll look up, or we'll figure out how to do 10 electrons next. So if it has 10 electrons, remember it's going to have 10 protons. So we'll go to our figure here, and we'll look up the element with 10 as an atomic number. We see that that's neon. So we're going to do the electron configuration here of neon. Okay. Start at the bottom and we go up. Remember, when we get to the P's, we do 1 before going back and pairing. Here we go. 1, 2, 3, 4, 5, 6, 7. Now we can go back and pair. 8, 9, 10. Okay? So let's go ahead and write each one of these out. And we're going to do what's called the expanded form first. And the expanded form lists each and every one of these lines separately. Each orbital gets its own spot in the configuration. So 1s has 2 electrons. 2s has 2 electrons. Remember, this one's called the px. So the 2p subscript x has 2 electrons. That's the py. So the 2py has 2 electrons. Here's the pz. 2pz has 2 electrons. So when we write out each and every one of the orbitals, this is called the expanded electron configuration. Expanded. Now we can recognize that all of these are p's, right? So we can group them together, and that makes a shortcut way of doing it. So we have fewer things to write. So the S's stay the same. 1s2, 2s2, but this time we're going to just write the 2 p's, and there's 2 plus 2 plus 2. There's a total of 6 electrons in that set of p orbitals. Okay? When we group those p's together, this is called the condensed electron configuration. So this is the expanded for neon, and this is the condensed electron configuration for neon. Now usually we aren't given the number of electrons for a particular atom. Usually we are given the name of the element, and we have to figure out how many electrons there are and what the electron configuration is. Not a problem, because we're just practicing that with our periodic tables. So let's say we want to do the electron configuration of carbon. Carbon, we look on our periodic table, we find the C. We see that the little number in that box happens to be a 6, which means that the neutral atom has 6 protons, and so then it has 6 electrons if it's neutral. And that's for the carbon. Alright, let's go ahead and bottom up. Let's keep going. 1, 2, 3, 4, 5, 6. We are done. So let's write out the electron configuration. We'll do 1s2, 2s2, 2px has 1 electron in it, only 1. The 2py also has 1 electron in it. Okay? So this is the expanded version. We can recognize that we can do a condensed version on this. 1s2, 2s2, 2p, this time will be 2, because there are 2 electrons in all of those p's. So expanded and condensed electron configurations for carbon. Let's go ahead and do another one. Let's try oxygen. Now go ahead while I'm erasing this whiteboard and look up how many electrons a neutral atom of oxygen happens to have. Okay, hopefully everyone has found that. We looked at our periodic table, we find the O. We look at the little number in there, 8, and it has 8 neutrons, therefore, 8 protons. And if it has 8 protons, it'll have 8 electrons in a neutral atom. Okay, so we're doing oxygen right now. Let's go ahead and count up to 8. 1, 2, 3, 4, 5, 6, 7, and we go back for the 8th. So the expanded version is 1s2, 2s2, 2p, x, which has 2 in it, 2py only has 1 in it, and 2pz only has 1 in it. Okay? P's we can put together in the condensed version. 1s2, 2s2, 2p, 2, 3, and 4. So 4. Okay? Electron configurations for oxygen. Let's go ahead and do sulfur. And erase our whiteboard here. Now sulfur on the periodic table is right under the oxygen. It has 16 protons. 16 protons means 16 electrons in a neutral atom. We're doing sulfur this time. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. And then we stop because we got to 16. Let's go ahead and write it. And we'll just do the condensed version here to make it go a little faster. 1s has 2, 2s has 2, 2p is filled, it's got 6, 3s has 2, and then 3p has 2, 3, 4. This is the electron configuration for sulfur, the condensed electron configuration. Okay. Now let's go ahead and do barium. Barium is the biggest one we'll do because in this class we don't actually deal with the F's. and filling the electron configurations involving Fs. You have to know the Fs has 7 orbitals and therefore can hold 14 electrons, but we won't go that far as to filling those up. So barium's as far as we can get before we hit the Fs. So barium's the one that, if you can do that one, you can do them all. So let's go ahead and work on that one. Barium has 56 protons. 56 protons means that in a neutral atom it has 56 electrons. So we're doing barium at this point. 56, that's a lot. So we're going to start at the bottom, move up, just like we said on all the others. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So right now I've got 18 filled in there. One thing to definitely remember is these overlapping orbitals. Remember, the 4s has lower energy than the 3d. So we have to fill the 4s before we go to the 3d. So after we finish the 3p here, we go to the 4s. So we were at 18. Let's keep counting up. 18, 19, 20. Now we can go to the 3d. 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. Okay, now we're at 30. Next energy level up is the 4p's. So we're going to go there. So this is 30, 31, 32, 33, 34, 35, 36. Now we're at 36. Still have to keep going because we've got to get up to 56. So the next energy level up we see are the 5 S's. Okay, 36, 37, 38. Now we go over to the 4 D's. 38, 39, 40, 41, 42, 43, 44, 45, 46, 47, 48. Oh, 48. We're not done yet. We got to get up to 56. So let's keep going. The next energy level up are the 5 P's. So we're going to fill those in. We're at 48. Let's keep counting. 49, 50, 51, 52, 53, 54. Next energy level up are the 6 S's. So we were at 54, 55, 56. 56 is where we stop. Now we have to pull them down and write them in our horizontal notation. Now we're going to only do the condensed version for this. We've got the 1s has 2, 2s has 2, the 2p has 6, they're right there. Then the 3s has 2, the 3p has 6, the 4s has 2, then we did the 3d. The 3d has 10, because it is completely filled. And after that were the 4p's. 4p has 6, then the 5s has 2, and the 4d's have 10. Now over here, we go up to this one. The 5p's have 6, and then the 6s ends up with 2. Okay? So this is the electron configuration of barium. You can see it's very long, even in the condensed version. So do make sure that you can do any of the elements up through barium. And the key for this is understanding our periodic table. Okay? And you might have thought that the periodic table has a sort of weird shape. But the shape reflects the electron configurations exactly. Okay? Let me show you why. The first row are the 1s's. Here's 1 electron in the 1s. He has 2 electrons in the 1s. Then the second row contains these guys. If you had 1 electron in the 2s energy level, you'd be lithium. If you had 2 electrons, you'd be beryllium. Now we go to the 2p's. They're over here. If you had 1 electron in the 2p, it'd be boron,